Hi, kitty. All right, emails are sent. Welcome to one more review. I'm guessing that the main topic of conversation will probably be activity 18, but I'm certainly willing to look at anything on activity 19, which I think I uploaded last night. Or if you have MyLab questions, you'll look at those as well. Good lesson for me is to make sure I erase the whiteboard when I'm done. Geez, I got stuck. So let me know what you got if you have any questions at all. Waiting for folks to get logged in. I'm going to make sure I have all those documents ready. Oh, now that I think about it, I don't have activity 19 loaded yet. We're working on a bunch of stuff for this class, but that's not one of the things I did. I was able to sort of put together a schedule of what we're going to do the rest of the semester, pretty much a day-by-day schedule. And I'm thinking I'd be able to stick with it really closely. Activity 19, yep, it's not posted yet, Matthew. I'll get that as soon as we're done here, I guess. I got busy this morning and made sure. I know I fell behind with the MyLabs. I did that this morning. I've had several visitors one way or another with, well, basically the basic algebra students have been logging in and working with me on Collaborate Ultra, getting some stuff done there. But when I end today, I'll make sure that activity 19 is up and ready to go. Maybe throw a few practice problems up. The whole session was definite integrals. So if I'm going to try to find the area under this curve, I can find it by plugging in the formula for that curve. In this case, it was f of x is x squared. Taking the antiderivative of that, then evaluate that between the low and the high number. So every time you get one of these definite integrals, if someone asks you what is a definite integral, the answer is it's a number. Every time we do a definite integral, we should get a number. It's representative of, in this case, it's representative of the area between x squared and then the x-axis. But every single time, that's just a number. A little later on, we'll look at areas between curves as well. So there's not just one standard idea for this, but every time you work a definite integral, it will work out to be a number. So there's always two steps in a definite integral. One part is to do the integral sign. Take the antiderivative of x squared, we get 1/3 x cubed, and then evaluate that from the upper limit, x equals 6, to the lower limit, x equals 3, and then evaluate the one minus the other. So if I plug a 6 in here, 6 cubed is, let's see, 36 times 2. I think that's 216. Yep. So this is 1/3 times 216. And this is 1/3 times 3 cubed, 1/3 times 27. 1/3 times 27 is 9. 1/3 times 216 is 72. Subtract the bottom from the top, it looks like there would be, what, 63 square units of area under that curve. 63 square units. So notice, and there's two really important ideas in this one. One of them is the area under the curve and the applications, and then the other is the average value. So if there are 36 square units in here, if you march each one of these out, each one of these boxes, one high, one wide, there'd be 63 of those. Notice that this is spread out over an interval of 3 units. We have a high value there of 36. That's the maximum value in the interval. We have a minimum value there of 9. So the average value has to be somewhere in between those two. And since this is 3 units wide and 63 square units, if we take 63 and divide it by 3, 21. The average height is 21. So if I go up here at 21, that's sort of the average height in that region in between 3 and 6. So here's 36, here's 21, down here is 9. Notice that 21 isn't right smack dab in between 36 and 9. And the reason it isn't is because this is a curve and not a straight line. So there's, as a little bit of a belly in there, the average falls closer to the bottom than it does to the top. So geometrically, what I can do is, that whole black shaded thing is 36 units. If I come across here and draw this rectangle that I guess I'll cross hatch the other way in green, that rectangle is also 63 units, right? It's 3 wide and it's 21 tall, right? So the general idea here is we can replace this thing that has all sorts of different values with one that has more of a constant value. And graphically, here's how we can come up with, if we're unable to do the calculations, here's sort of how we can come up with this average value spot. Okay, so the takeaway on this is over here we have some of this area on the average part, which is above the function. And on the other part over here, we have some area above the average part that's under the function. And these two little parts, I'm going to call that part right there part A, and that part right there is part B. If I had a really accurate graph, those two parts would be exactly the same. So the area in this rectangle would equal the area that's shaded in black here. So, certainly that stuff that's both crosshatched both ways, that has to be equal. So this little green spot here that's only green has to be the same area as that spot that's only black. And that's going to come in handy a little later on when we're working with some applications. So that's something to have a good look at. So let's work at maybe one or two more of these definite integrals and relate those to the area under the curve. Maybe to illustrate that idea, let's do one that's a nice straight line. Let's consider the integral, how about from 1 to 5 of 3x minus, we'll go 3x plus 2 dx. So we have a slope of 3 and y-intercept 2. Starts right there. So that's the order pair 0, 2. By the time we get out here to 5, we're at 15 and 17. Here's the 5, 17. 1, I plug in a 1, 3, 4, 5, 1, 5. So this is the area that definite integral will allow me to calculate. It'll be this area from 1 to 5 underneath the function y equals 3x plus 2. So a couple of ordered pairs here that I know. The very first one is when I plug in a 1, I get back a 5. And the other one is when I plug in a 5, I get back a 17. Okay. So let's calculate the area. Actually, we could do the calculate the area in two ways on this one. Let's do it first off with a rectangle and a triangle. And then after that, let's do it using calculus just to show you that they come out the same. So if I make this little rectangle down here, it's what, 4 wide and 5 high. So this rectangle has 20 square units in it. Okay. And then we have the triangle above it. Let's see, the height of this triangle goes from 5 to 17. So the height of that triangle has to be 12. It's still 4 wide, so 1/2 base times height would yield what, 48 times 1/2 would be 24. So 24 square units here. Grand total of 44 square units. That's what that area under the curve above the x-axis should contain. Let's go through it using calculus, see if we get that same answer. 2 steps, take the antiderivative. Let's see, 3, keep the x, raise the power, reciprocal of the new power. Antiderivative of 2 is 2x. I don't need to put the plus c at the end of these because when I figure out with 5 and figure out with 1 and subtract the 1 from the other, I end up canceling that c out. So 3/2 x squared plus 2x evaluated from x equal to 5 to x equal to 1. Do the 1 first. This is 3/2 plus 2. Okay. Figure out the 5 next. 5 is 25 times 3 is 75. So this is 75 halves plus 50. Okay, I'm going to do the subtraction. Remember to subtract like terms. 75 minus 3. This would be 72 halves. 50 minus 2 is plus 48. So I end up with 36 plus 48, which is 84 squared. Whoops. 36 plus 48 is 84. Before I had 44. Oh my goodness, what went wrong? 4 wide, 5 high, that's 20. 15, 17, 12 high, 2 wide, that's 24, that's 44. Do a subtraction wrong? Oh, here it is. Jeez. Okay, yeah. Plug in a 5. This is a 10. Woo! There we go. All right, they're both 44. Calculus made it a little more difficult, didn't I? Okay, so plug in a 5. This is 75 halves. Plug in a 5 here. It's a 10. Plug in a 1 down here, 3 halves and 2. Subtract those from above. 75 halves minus 3 halves, 72 halves. 10 minus 2 is just 8. To that addition, sure enough, it's 44 square units. Either way we did it. Now let's make sure that the average value makes sense here. So in this case, we had a nice straight line. We had a nice straight line from here to here. Absolutely perfectly straight. And since that's absolutely perfectly straight, we should be able to take the number that's right smack dab in between this height of 5 and this height of 17. 17 plus 5 is 22. Half of that is 11. So the average height should be 11. So 5, 6, 7, 8, 9, 10, 11. Right across here is where we draw my average height line. Okay. So I'm going to again shade the region in black, the area under the curve, those 44 square units. There they are. So that area, 44 square units, should have the same as this area under this rectangle. So how am I going to get that without having to even think about it? Well, I know there are 44 square units under the curve, which means if I'm going to replace this curve with a straight line across here for the average value, I still have to have those 44 units. Okay, it is 4 wide. So if it's 4 wide and it has 44 square units, length times width is the area. Area is 44, width is 4. Therefore, the height must be 11. Again, smack dab right in between 17 and 5. But that only works if that's a straight line. Okay, so that's sort of how we figure those out. I apologize for not getting activity 19 up. I guess it slipped my mind. I had a lot of stuff going on this morning, and gosh, I thought I had it done. I know I looked at it, but I'll go and post that now. So you have a chance to look at least a little bit before class tomorrow. We'll work on that again in class tomorrow. Make sure I posted a little chart that shows exactly when everything is due. So there's no more questions about when the MyLabs are due or when the activities are due. Everything should, from this point forward, go fairly smooth on that, right? So I'll get that done and I'll talk to you tomorrow.